Welcome to today's paper reading. Today's paper is titled, Diffusion Models Are Real-Time Game Engines. This paper was published on the AR14 preprint by Dani Valevski and colleagues from Google Research. GameNGen is the first game engine powered entirely by a neural model, enabling real-time interaction with complex environments over long trajectories at high quality. It can simulate the classic game Doom at over 20 frames per second on a single CPU. The next frame prediction achieves a PSNR of 29.4, which is comparable to lossy JPEG compression. Human raters are only slightly better than random chance at distinguishing short clips of the game from clips of the simulation. The training of GameNGen involves two phases. First, an RL agent learns to play the game and the training sessions are recorded. Second, a diffusion model is trained to produce the next frame, conditioned on the sequence of past frames and actions. Conditioning augmentations enable stable autoregressive generation over long trajectories. Figure 1 illustrates a human player engaging with the classic game Doom through GameNGen, which operates at a frame rate of 20 FPS. This demonstration highlights the real-time interaction capabilities of GameNGen, showcasing its ability to simulate complex environments in high quality. For a visual demonstration, please refer to the provided link for demo videos. The core of computer games is the game loop, which consists of three main steps: gathering user inputs, updating the game state, and rendering it to the screen. This loop runs at high frame rates to create the illusion of an interactive virtual world. Recently, generative models have made significant progress in producing images and videos based on various inputs, with diffusion models becoming the standard in media generation. However, simulating interactive worlds in video games presents unique challenges, such as the need for autoregressive frame generation, which can lead to instability and sampling divergence. Additionally, complex game state updates, such as managing health and ammo, attacking enemies, and opening doors, must be handled efficiently. This work aims to address these challenges by demonstrating that a neural model can simulate a complex game like Doom in real time with high visual quality. Figure 2 presents a comparison of GameNGen with previous state-of-the-art simulations of the iconic game Doom. The figure highlights that GameNGen can simulate Doom in real time at 20 frames per second, maintaining a visual quality that is comparable to the original game. It also demonstrates the model's capability to perform complex game state updates such as health and ammo tallying, enemy attacks, object damage, door openings, and the persistence of the game state over extended periods. This comparison underscores GameNGen's advancements in real-time neural game simulation. The interactive environment E is defined by a space of latent states S, a space of partial projections O, and a partial projection function V mapping S to O. Additionally, E includes a set of actions A and a transition probability function P, S, A, S, that governs state transitions given actions. For instance, in the game Doom, S represents the program's memory, O the rendered screen, V the rendering logic, A the player inputs, and P the game logic responding to these inputs. The interactive world simulation aims to minimize the expected distance between observations from the environment and the simulation under a given policy pi, which determines actions based on past observations and actions. The training of the generative model always employs the teacher-forcing objective, where the environment E is simulated by autoregressively sampling observations. Figure 3 provides an overview of the GameNGen method, which is a generative diffusion model designed to simulate games. The figure highlights the process of collecting training data through an agent playing the game, which is then used to train the generative model. The model conditions on the agent's trajectories, which include sequences of actions and observations. The V prediction details are omitted for brevity, focusing on the broader methodological approach. GameNGen, a generative diffusion model, collects training data by having an agent interact with the environment. The agent's actions and observations during training form the dataset tagent, which is used to train the generative model. This model is conditioned on the tagent trajectories and is based on Stable Diffusion version 1.4, with modifications to minimize the diffusion loss. During inference, the model uses DDM sampling with classifier-free guidance and employs only 4 denoising steps for efficiency, achieving high-quality results. There is also potential for parallel frame generation to increase image generation rates. Figure 4 illustrates the phenomenon of autoregressive drift in a 50-frame trajectory where the player remains stationary. The top section shows that the quality of the frames degrades rapidly after 20 to 30 steps. In contrast, the bottom section demonstrates that applying noise augmentation to the frames effectively mitigates this degradation, maintaining consistent quality throughout the trajectory. The agent model is trained using the Proximal Policy Optimization (PPO) algorithm, which employs a convolutional neural network (CNN) as its feature network. This setup is facilitated by the Stable Baselines 3 infrastructure. The agent is provided with downscaled frame images and in-game maps, each at a resolution of 160 by 120 pixels, and has access to its last 32 actions. The feature network computes a 512-dimensional representation for each image. The actor and critic networks are multilayer perceptrons, MLPs, built on top of the image feature network and past action sequence outputs. The generative model training begins from a pre-trained checkpoint of Stable Diffusion 1.4, with all UNet parameters unfrozen. Training uses a batch size of 128 and a constant learning rate of 2 times 10 to the power of -5, employing the Ada factor optimizer without weight decay and gradient clipping set to 1.0. The diffusion loss parameterization is modified to V-prediction, and context frames are conditionally dropped during training to allow for classifier-free guidance, CFG, during inference. Figure 5 presents a comparison between the model's predictions and the actual ground truth frames. Specifically, it highlights the last 4 frames of the past observations context. The image quality metrics for these comparisons are provided, showing a PSNR of 29.43 and an LPIPS of 0.249. These metrics indicate the model's performance in terms of image fidelity and perceptual similarity to the original frames. The results show that the simulation quality is comparable to the original game, especially over long trajectories. For short trajectories, human raters can only slightly distinguish between the simulation and the actual game. In terms of image quality, the model achieves a PSNR of 29.43 and an LPIPS of 0.249, which is similar to lossy JPEG compression with quality settings of 20 to 30. For video quality, the model's FVD scores are 114.02 for 16 frames and 186.23 for 32 frames, indicating that per-frame metrics decrease over time due to the accumulation of small differences in movement velocities. Figure 6 illustrates the autoregressive evaluation of PSNR and LPIPS metrics over 64 steps. The predicted and ground truth trajectories often diverge after a few steps due to the accumulation of small differences in movement velocities between frames. This divergence results in a gradual decrease in PSNR and increase in LPIPS values, highlighting the limitations of per-frame metrics in capturing the overall similarity in content and image quality between the predicted and actual game trajectories. Table 1 illustrates the effect of varying the number of history frames used as context on the PSNR and LPIPS metrics. The context length ranges from 1 to 64 frames, with 8,912 test set examples from 5 levels being used for evaluation. The results show that both PSNR and LPIPS metrics generally improve as the number of history frames increases, indicating better generation quality with longer context lengths. Figure 7 illustrates the impact of noise augmentation on model quality through average LPIPS and PSNR values for each autoregressive step. The data clearly shows that without noise augmentation, model quality degrades rapidly after 10 to 20 frames, as indicated by the increasing LPIPS and decreasing PSNR. In contrast, the use of noise augmentation effectively prevents this rapid degradation, maintaining higher quality over the same number of frames. In the field of interactive 3D simulation, game engines like Unreal and Unity are widely used for real-time rendering and processing of visual and physical effects. These engines rely on efficient heuristics rather than physically accurate simulation to maintain high frame rates. Neural 3D simulation has seen significant advancements with methods like NeRFs and Gaussian splatting, which offer impressive reconstruction results but are often limited to static scenes. Video diffusion models have achieved state-of-the-art results in text-to-image and text-to-video generation, though they remain too slow for real-time applications. Table 2 presents a comparison of model performance on different difficulty levels, specifically easy, medium, and hard splits of a dataset. The models were trained using data generated by an agent and by a random policy. The performance metrics, PSNR and PIPS, were computed for each trajectory on a single frame after 3 seconds. The table highlights the differences in performance between the agent-generated and random-generated data across these difficulty levels. In this discussion, we summarize the introduction of GameNGen, highlighting its capability to achieve high-quality real-time gameplay at 20 frames per second using a Nero model. We also outline a method for converting interactive software like computer games into Nero models. However, we acknowledge significant limitations, such as the model's limited memory, which only allows access to a little over 3 seconds of history, and the remaining differences between the agent's behavior and that of human players. Looking ahead, we propose future work to test GameNGen on other games and interactive software systems, address the Doom-specific reward function, and optimize the model's memory usage and frame rates for better performance on consumer hardware. Thank you for watching.